Every few years, Mount Etna reminds the world why it is Europe's most active volcano. Towering lava fountains and ash clouds make international headlines. But scientists are becoming increasingly concerned about a far more dangerous process that almost nobody can see. The entire eastern side of Mount Etna is slowly sliding into the Mediterranean Sea, not by meters each day, but by just a few centimeters each year. It sounds insignificant until you realize this movement involves hundreds of square kilometers of an active volcano. For decades, researchers believed rising magma was pushing the mountain apart. Now, groundbreaking discoveries beneath the seafloor have revealed something even more unsettling. The question is no longer whether Etna is moving. The question is how this extraordinary geological story will ultimately end. Standing more than 3,300 meters above sea level and spanning an area of roughly 1,200 square kilometers, Mount Etna is Europe's largest volcano. Its frequent eruptions have shaped history, destroyed villages, enriched farmland, and transformed the lives of countless generations who continue to live on its slopes. To understand why this volcano is moving, it is first necessary to understand how it formed. Unlike volcanoes such as those found along the Pacific Ring of Fire, Etna does not sit directly above a classic subduction zone. Instead, its existence is tied to a remarkably complex tectonic environment where the African plate slowly pushes beneath the Eurasian plate, while numerous faults stretch and fracture the crust beneath Sicily. Over hundreds of thousands of years, repeated eruptions stacked layer upon layer of lava, ash, volcanic debris, and pyroclastic deposits, gradually building one of the largest volcanoes in Europe. As Etna continued growing, however, another process quietly unfolded beneath it. The volcano became incredibly heavy. Millions upon millions of tons of volcanic rock accumulated upon foundations that, in many places, consist of comparatively weak sedimentary rocks and ancient marine deposits. Today, every second of every day, the eastern flank experiences a subtle downslope pull. Every new lava flow makes the volcano just a little heavier. Every eruption slightly changes how stress is distributed within the mountain. Over thousands of years, these tiny movements accumulate into something enormous. Entire sections of the volcano begin creeping seaward. Scientists refer to this phenomenon as flank instability. Rather than behaving as one solid mountain, Mount Etna consists of numerous blocks separated by faults and fractures. These blocks move at different speeds, but together they form an immense unstable sector occupying much of the volcano's eastern and southeastern flank. Before we continue, don't forget to click on that subscribe button and like this video, as it's the best way to support this channel. For many years, the dominant explanation focused on magma. Mount Etna is one of the world's most active volcanoes. Beneath its surface, magma constantly rises through fractures before erupting as lava or remaining trapped underground. Researchers believe these intrusions acted like hydraulic jacks. As magma forced open cracks within the volcano, it pushed the eastern flank outward. According to this interpretation, the volcano expanded during periods of heightened volcanic activity before stabilizing once eruptions subsided. This theory matched many observations. Periods of increased deformation often coincided with eruptions. Earthquake swarms frequently accompanied magma movement. Faults became more active as volcanic pressure increased. It seemed logical that magma was the engine driving the volcano's slow collapse. But there was a problem. Movement sometimes continued even when the volcano remained relatively quiet. Something else appeared to be pushing the mountain. The breakthrough arrived in 2018 through an ambitious international research project known as GOC. Scientists from Germany's Geomar Helmholtz Center for Ocean Research, Kiel University, and Italy's National Institute of Geophysics and Volcanology realized that nearly all previous measurements had one important limitation. They stopped at the coastline. If the eastern flank truly continued beneath the Ionian Sea, then researchers needed to measure movement offshore as well. To accomplish this, they deployed an array of acoustic transponders directly onto the seabed east of Mount Etna. Unlike GPS stations on land, These underwater instruments could precisely measure the distance between fixed points on the ocean floor, allowing scientists to detect even tiny changes over time. The results transformed scientific understanding. During an 8-day period in May 2017, an offshore fault slipped by more than 4 centimeters. At nearly the same time, similar displacement occurred along the nearby coastline. The movement wasn't confined to the volcano above sea level. It continued beneath the sea. Even more surprising was what happened next. The submarine portion of the flank continued creeping even during periods when volcanic activity remained relatively subdued. This suggested that magma alone could not explain what scientists were observing. Instead, gravity itself appeared to be pulling the entire flank toward the sea. The GeoC findings fundamentally changed how researchers view Mount Etna. Rather than magma creating the movement, gravity now appears to be the dominant long-term driving force. Magma still matters enormously. Intrusions beneath the volcano can accelerate movement, trigger earthquakes, and temporarily increase deformation. But they are increasingly viewed as accelerators rather than primary drivers. Gravity is always acting. Magma occasionally adds another push. The distinction is critically important. If gravity alone is capable of driving flank motion, then the movement will continue whether or not the volcano is erupting. Etna is not simply responding to volcanic activity. It is gradually reorganizing under its own immense weight. Although today's movement is slow, geology reveals that Etna's past has included far more dramatic events. Approximately 8,000 years ago, the volcano experienced a massive collapse affecting its eastern flank. Enormous volumes of volcanic material suddenly failed, producing a huge submarine landslide that extended into the Ionian Sea. Scientists believe this collapse generated a powerful tsunami whose deposits have been identified across parts of the eastern Mediterranean. The event also contributed significantly to the formation of the Val del Bove, the vast horseshoe-shaped depression cutting deeply into Etna's eastern side. Although later eruptions and erosion continued modifying the landscape, evidence suggests that catastrophic flank failure played a major role in creating the features seen today. This ancient collapse serves as a reminder that volcanoes can undergo profound structural changes over geological timescales. What occurred thousands of years ago demonstrates that flank collapse is not merely theoretical. It has happened before. So, could it happen again? This is perhaps the most difficult question scientists face. The honest answer is yes. A future large-scale collapse is physically possible, but possibility should not be confused with probability. Researchers emphasize that there is no evidence indicating such an event is imminent. Current observations show continuous slow deformation rather than the kind of accelerating instability that might precede a catastrophic failure. Nevertheless, the hazard cannot be ignored. If an exceptionally large portion of Etna's eastern flank were to suddenly collapse into the Ionian Sea, enormous amounts of rock could displace seawater and generate a tsunami. Exactly how large such a tsunami would be remains uncertain. Computer simulations produce different results depending on assumptions about the size, speed, and geometry of the collapse. Some models suggest impacts concentrated around eastern Sicily. Others indicate waves capable of reaching southern Italy, Malta, Greece, and parts of the eastern Mediterranean. Because no modern collapse of comparable scale has occurred at Etna, considerable uncertainty surrounds every scenario. For this reason, scientists describe catastrophic flank collapse as a low probability but high consequence hazard. It deserves serious attention precisely because of its potential consequences, even if the likelihood remains low. No one knows exactly how Mount Etna's story will unfold. It could continue creeping toward the Ionian Sea at just a few centimeters per year for thousands of years, with periodic eruptions temporarily accelerating movement before the volcano settles back into its slow, relentless slide. Or future changes in magma supply, fault activity, or regional earthquakes could alter the pace of deformation in ways scientists cannot yet predict. That uncertainty is precisely why Etna remains one of the most closely monitored volcanoes on Earth. Advances in satellite imaging, seafloor monitoring, GPS networks, and fault creep meters are giving researchers an increasingly detailed picture of how the volcano behaves. Every eruption, every earthquake, and every millimeter of movement adds valuable data that improves our understanding of one of nature's most complex geological systems. While there is no evidence that a catastrophic flank collapse is imminent, scientists agree that the ongoing instability cannot be ignored. For now, Mount Etna continues to do what it has done for millennia: erupt, grow, and slowly reshape itself under the constant pull of gravity. Its future remains uncertain, but one thing is clear: Europe's largest volcano is far from a finished landscape. It is a living mountain, still evolving before our eyes, 1 centimeter at a time.